So this item right here, really important. Okay, that idea there. And you ran across that when you did that one worksheet where you guys all didn't do your homework? That's how you find the electric field? No, you haven't. No, you haven't. No, you haven't. The very first worksheet, I don't know, it was We the People, something or other, you guys did nothing. You came in, it was all blank. This was the worksheet where you would have done this like 15 times and said, okay, I'm bored with this. Yeah, I did it for you, so therefore I don't know if you know that. But that's an important formula to have. Okay, so then the next question is, so I go ready to integrate this, and now let me point out something that's going to happen to us in a moment. We're going to integrate. So we go V equals the integral of E dr. Well, we know that, therefore, the integral of, what was the formula we just came up with? KQ over R squared. I'm going to make that over R squared dr. Actually, no, I should make that singleton R. So make this R to the -2 so we can do it. Does that make sense? Everyone with me so far? Good? Everybody good? Okay. So then I'm going to go, I can plot the K, I can plot the Q, because those are going to be boring, they'll be constants. It's the integral of R to the -2 dr. So this becomes KQ negative, I can pull up the negative again. And I get R to the -1, right? Because I raise the power by 1 divided by the power you get, would be equal to my voltage. What's the problem with this, Natalie? I'm going to divide by 0. We just said it starts at best. Logically, we'd want to start at 0 and go to whatever. Is that going to work in this case? That's a problem. I have infinite negative potential energy. In other words, if I could start a positive charge and negative charge on top of each other, what would I get? Cataclysm. I'd have infinite negative energy. They can't start on top of each other. So we need a better system than starting on top of each other. So how are you going to set it so that, therefore, we can have potential energy, which is a concept we like, but not deal with this catastrophic, everybody's on top of each other thing? Colin, you got a suggestion for us? Thank you. That's exactly the right suggestion. We're going to say at infinity, the amount of potential energy is going to be 0, because if I put it in this formula, I get 0. And therefore, everything's got potential energy less than 0. That's why it's negative. That's how far you are down from 0. Does that make sense? Well, they're in you with me? Yep. So if I ask what your potential energy and location is, you're going to say relative to what spot in space? Infinity, where it is 0, right? Yeah.
Well, did you just say like a minute and a half ago that positive infinity is where the potential energy, or infinity is where the potential energy is placed?
Right, and it's going to have 0 there. And from there, it's downhill, just like we do with gravity.
Oh.
Right? So everything's going to have negative potential. Potential energy is always going to be negative. And if I want to know between two spots in space, I'm going to subtract one from the other, and that's how I get a positive potential energy, because I raised it from some place to the next place up.
Okay.
Right? Okay. So how much potential energy is vested in a -2 Coulomb test charge? This is 10 meters from a 10 Coulomb positive charge. So here we go. You ready? I'm going to go voltage is equal to the integral from where to where am I going to integrate this thing? From 10, not from 10 to, but from where to where? God, it was really quiet. I'm going to go from negative infinity. We were trying to avoid 0 like the plague, right? Negative infinity to 10 of KQ over R dr. Right? That's my electric field formula for a singleton charge. Sorry, my voltage, that's my electric field, sorry. So my voltage difference between infinity and 10 would be, I'll let my electric field like that, right? Electric field's got the R squared on the bottom staff, which is always going to give me, for a singleton charge, it's going to give me KQ over R, right? for a singleton charge. Okay? So my voltage difference between infinity and there would be negative 9 times 10 to the 9th. My charge would be negative 2. All the distance between them, which is initial is r, right? I'm going to plug in negative infinity, and I'm going to plug in 10. Plug in 10, I get that my voltage would be, this is 1.8 times 10 to the 910 over 10 minus 1.8 times 10 to the 10th over infinity. What's it going to be at infinity? 0, so that's always going to fall off. And I get my voltage is 1.8 times 10 to the 9th in this case. Now, that's a lot of work, when if you just plugged it in there, you would have gotten that answer. Right? Because infinity is always going to cancel out. Yes, ma'am? The way you do the voltage is it's the integral of the electric field dr, right? I integrate. It's always going to be this one, though, right? The singleton charge is always going to lead to this mess. Yes, if it's a singleton charge. Now, if I give you electric field as some sort of a strained zony thing, then you can't. Okay? Make sense? All right. Okay. All right, and that's my voltage. How do I figure how much potential energy I've invested, or how much potential energy it has when it gets there? What's my formula for energy? Potential energy.
V equals negative QK over R.
Oh, I screwed this up. This should have been a 10. Because we're moving it with a 10. The 10's with the center. I'm moving the negative 2 chest charge, right? There we get that? To the 10. Now, this is what's creating the field. This is what I'm moving around, right?
Yeah.
How much electric field do I have in that? So this should have been a freaking 10. Which means the 10's cancel it out. I would have got 9 times 10 to the 9th volts. Then how do I figure what the potential energy is? VQ equals U. My voltage is 9 times 10 to the 9th times Q, which is 10. No, it's going to be 2. Now we're moving the 2 around, right? In the field. Either way, by the way, you're going to get 1.8 times 10 to the negative 10 joules. That was the key. Right? Because if you talk about how much potential one have, the other one has the same potential energy to live from infinity. All right. That's been fun. All right. Everybody tried what?
Would we carry the negative?
Yeah, so there should be a negative on this. Down from 0. So how far we are down from 0. Okay?
So we integrated with my voltage, and then using the voltage, we multiplied it by charge to find our energy.
Right. Now again, there's some shortcuts along the way. That's the voltage. We already know what it's going to give us when we plug in our negative infinity and 0 and 10. It's just going to give us this without the other part's always going to be 0, right? So we can just go right to this, find the voltage. Once I have the voltage, multiply it by the charge, and get how much potential energy you have there. Okay? So there's some shortcuts along the way. Yes, ma'am. You should be a lot confused because I did that poorly. Okay. So let's...
So from the second to the third step, you plug in 10 as the charge. Yeah, that's it.
No. The 10's in there. Yes, I plugged 10 for charge because we were talking about moving the negative 2 charge. We're talking about moving this one. The 10 charge is what's sitting in the center of my field.
So you do the one that's stable.
That's the one that's creating the voltage around it, right? And the electric field around it. So that's the one I should have started with because I was talking about moving the negative 2. Now, to be frank, it doesn't matter. If this was the negative 2 and then I put it multiplied by 10 at the end, or if this is the 10 and negative 2, it shouldn't change how much potential energy is available there, right?
Quick question.
Yes.
So as long as the charge in your voltage integration is proportional
No. They're multiplied.
Yeah. Okay.
So if I had used 4 and 5, I would have got the same.
I'm just kind of confused on how it doesn't matter.
If you have 4 and 5, the net charge between the two of them is the same, right? You're talking about, but when you talk about the force between them, 4 and 5 use the same force as 10 and 2.
Really?
KQQ over D squared,
Okay.
right?
Yeah.
So they're the same numbers. The force, the work being done moving them around has to be the same because the force is the same, right? And the distance is the same. So therefore, the voltage is going to be the same because that's how much energy you're making.
Okay.
Right.
So
as long as those two multiply together, you're going to get the same answer.
So voltage is just an interesting way of saying force in this chapter?
No, voltage is an interesting way of saying everything about potential energy except for the charge. Voltage is what charge your battery. It says 9 volts. If I say how much charge going from one to the other, that's how much energy you have there. It is more akin to potential energy. That's why they're calling it potential difference now. It's like potential energy. It's everything potential energy except for how much charge you're dragging around inside the field. That's great. His hand was next.
Yeah, so in your third step,
Uh-huh.
we got our negative K, but then on the fourth step.
Oh, you're right. That should have been negative,
So then would we
which would have made this negative, which would have made this positive, which would have wanted to be anyways. Thank you. Yes?
So in the third step, you plugged in 10.
Uh-huh.
And at the end, you did 2.
Plugged in 2.
So you're saying it doesn't matter because they just have to be different.
If I put a 2 here and put a 10 here, I'd have got the exact same answer, which makes sense because the question is how much potential energy do I make when I separate these two particles? Well, does it matter which one I moved? I could have said the field is being created by a 2, which makes a 10 here.
But you can't just use 2 in both places because that would mean it would be.
Right, because then you're saying what's the field of 2 is on a 2, and 2 on a 2 is not what's happening. It's a 10 on a 2 or a 2 on a 10. Doesn't matter which is on which, but they have to give you the same answer.
So I can't really tell, but did you make one of the charges specifically negative?
Yes, I made the 2 is negative. All right, now, real quickly, anybody notice what formula I got them? The potential energy is equal to K Q over D, right? Because of this, over R, right? Times Q, right? Well, it's just one R, right? Because there's one R down here. So it's this times this, right, that we ended up with? Well, negative, yes. Does that look familiar? Yes, because potential energy for gravity, this electric field, potential energy for gravity is G M1 M2 over R with a negative out in front. And yes, it goes to infinity. So my potential energy formula can be gotten directly this way without dealing with voltage at all. As long as we're talking about a single point charge, right? They both had to be single point charges for this to work.
So one thing and another thing.
Right. One charge, one charge. If you got any other things going on, this is gonna work. If you're talking about charge plate, things fall apart. Talking about electric field described by me writing equations on the wall. It falls apart. Okay? But this is the potential energy formula for two charged particles. That's an interesting question. You and Einstein would have the same argument. Same discussion. No, I'm saying you had the same discussion. Einstein spent his last days trying to figure out why these are the same. He was 100% convinced they were the same. He was 100% convinced that all the force in the universe were the same force, just we were looking at it with different lenses. And the seat that Hawking has is his job, according to that seat, to prove that all the forces are the same. He hasn't done diddly squat, but his seat on whatever college he's at, that seat is reserved for whoever is trying to prove Einstein's theorem that all the forces are the same. They all look the same.